So all these people gave some conditions for this guy to exist, and in some of them, actually in all of them, there is a representation for this law, okay? And there is one that I want to mention today, because when the expected value of psi1 is finite and is strictly positive, then P0 plus can be written as, so if you take P0 of f xt1 fn xtn, so if you take the finite dimensional distributions of this guy, so this can be written as mu t of dx1, mu t1, and then the semigroup of f2 of x1, so I will write it as f x1, and then the expected value starting from x of f x t2 minus t1 up to fn of xtn minus t1, okay? That is just telling us that under P0 we still have the Markov property. That is true in general because of the way we build this P0. But the thing that is important is that this measure is such that mu t dx, so let's say mu t dx for t positive, strictly positive, that's important, is an entrance law for x, so meaning that mu t dx of the expected value of f of xs is equal to mu t plus s of dx of x of f of x, okay? It's like the semigroup property, okay? And furthermore, the expected value of f of xt, okay? So this is the integral mu t dx f of x, can be written as 1 over the mean, and that is why this is important to be strictly positive, and then the expected value of f of t to the 1 over alpha, and then a random variable I hat, 1 over alpha, 1 over I hat, where I hat is the exponential functional of minus alpha psi s ds, okay? With psi being such that x is the Laplace transform of psi, okay? And this is the first place where we see that these exponential functionals, well, the second place where we see that these exponential functionals are related to the law of x. The first place, of course, is the first heating time of 0, okay? This is the second place where we see exponential functionals appearing, okay? But in fact, if we look at the theory of self-similar processes, of positive self-similar Markov processes, exponential functionals are everywhere. they appear as the first heating time of 0. They appear in entrance loads, okay? But they also appear in the asymptotic behavior of X, and in many other places, like first passage times, above a level. They appear also as quasi-stationary distributions of X, and so on. Okay? There are many, many instances where exponential functionals appear in the theory of self-similar processes. Okay? That is one of the reasons for studying these random variables, but there are many other reasons. Okay? Yeah, one thing that I wanted to mention before going to the next topic is that there is one reason why it is natural that exponential functionals appear in the description of the asymptotic behavior of X. And that is, well, here exponential functionals are related to the existence of this limit that is here. Yes? Okay. So this exponential functional that is here, okay, is related in the existence of this guy. Okay? But remember, starting from X is the same as multiplying by X and time changing by X to the minus alpha, and starting from 1. Yeah? Okay, so make X go to 0. What is happening with the time in here? The time is going to plus infinity. Yeah? And so it's happening with this guy to the minus 1. Okay? So in fact, this is also related to the asymptotic behavior of xt by t to the 1 over alpha. Okay? And so this is one evidence why the asymptotic behavior of X should also be related to exponential functionals of Lévy processes. Okay? And there are some laws of iterated logarithm, for instance, that are given for X in terms of exponential functionals. Okay? Okay. But exponential functionals are in other domains. Appear in finance, risk theory, time series, statistical physics, and in many other fields. Okay? So you can actually check a survey by Bertrand and your improbability surveys. Okay, and they give many examples of exponential functionals appearing in these fields or other fields. Okay, and there is something that is important here, is that studying these random variables is a very difficult matter. And why it is difficult? Even to simulate these random variables is difficult because we need to study the whole path of the process and then integrate it. Okay? So we need to find some tricks to study these random variables. Okay? So we need to develop tools to study exponential functionals of Lévy processes. Okay. So to get either the explicit law or get the asymptotic behavior or estimates for the distribution obtain distributional identities or properties as, for instance, infinite divisibility or other questions. Okay? And this is what I want to do now. I want to give you some ideas of some tools that are in the literature to get some information about these random variables. But they are not, of course, they are not covering all the cases. And there is a topic that is even harder, is when you take psi and y, a bivariate Lévy process in R2, okay, and you define the exponential of psi t driven by y, okay. That again has a lot of applications, particular in time series, but it appears in many other fields, okay, and it is necessary to get information about this. All the questions are pertinent for that those random variables, okay. And yeah, I mean, there are a few papers around related to this, and in particular, there is a very interesting paper by Alex Linder and Sato, okay, that have some information about those random variables, and there you can find many references for these exponential functions. Okay. So I was just discussing with Professor Sato about, they studied in particular the infinite divisibility property of this guy, or some equivalences of that, or some related questions around that. Okay. So now I will speak about these random variables. Okay, so we take psi. For the rest of this lecture, we will take psi to be a Lévy process that either has a finite lifetime, okay, so that is what I call Q strictly positive, because Q is the character, the parameter of the exponential, or Q is equal to 0 and psi goes to minus infinity as t goes to infinity. Okay? And those conditions are necessary and sufficient for the random variable exponential psi s ds to be finite almost surely. These are the only cases on which the exponential functional can be finite. Okay? And this is because psi, when it goes to minus infinity, it goes in a linear way. Okay. These exponential functionals, although they are difficult to study, they have several properties. And one interesting property is that they can be studied as perpetuities. Okay. So if we take t a stopping time of psi with respect to the filtration built by psi, then we will have that I can be written always as the integral between 0 and t exponential alpha psi s ds plus the exponential of psi at the position t, indicator t being finite, and then the integral from 0 to infinity of exponential of psi s plus t minus psi t ds. Okay? It's just write the integral between 0 and infinity as the integral between 0 and t and infinity. Okay? This is the first one. The second one, you multiply and divide by this guy, okay, and you get this expression and a change of variables. Okay. Well, by the strong Markov property, this that we have on the right is independent of what we have on the left. Psi q given by the integral from 0 to t exponential psi s ds, and m given by the exponential of psi t when t is finite, are independent of the integral from 0 to infinity of exponential of psi s plus t minus psi t ds, okay? And this guy has the same law as I. Okay? So we have that I can always be written as Q plus M times I tilde, okay, with Q M independent of I tilde, and I tilde being equal in law to I. Okay? By a perpetuity, we mean a random variable that satisfies this kind of random equation. Fixed point random equation. Yeah? Okay. And those perpetuities appear in finance in particular. And this, in fact, is something that is very simple but very powerful, because we have the freedom to use any random time. Yeah? Okay. And that is quite nice. So one point is that the theory of perpetuities of Goldie and other authors is available for the study of exponential functions. And something else, we have freedom to choose t. Okay? So, for instance, t can be taken as tau t, which is the first time where the exponential functional goes above t, okay, for some t strictly positive. And when this is empty, just take it as infinite. Okay, it's the time change that we saw in Lamperti transform. Okay, so that makes that we can write I like t plus the exponential of psi of tau t, and then I tilde indicator tau t finite. Yeah. Okay. So this is t plus xt I tilde, where x is the Lamperti transform of psi. Okay, that is one of the things. So this tells us, okay, that if we know something on x, then maybe we can transfer it into something on I. And vice versa. If we know something on I, then we can transfer it into something on x. Okay? In particular, one can verify that there exists a function g from 0 to infinity into 0 infinity, and the measure mu non-degenerate such that xt divided by gt So the probability starting from a point 1 is in dy, given that t is smaller than t0. Okay? So remember t0 is the time where this this time change explodes. Okay? Such that this converges to a mu dy. Okay? If and only if there exists a measure lambda tilde dy such that the probability of I minus t divided by gt is in dy, okay, when t is smaller than I, converges to lambda dy. Okay? And the reason is that if we have this, because this is independent, we can put it in the product and then get something for the difference. Okay? And the reciprocal is true. If we know this, then we have something for the product, okay? And by some properties of the characteristic function of this random variable, we can split that limit and get something just for xt divided by gt, okay? And this is what is called the Jacob limit of x, okay? And this happens if and only if I is in the domain of attraction of maximum, in the maximum domain of attraction of an extremal distribution. So we say that a random variable is in the domain of attraction of a stable distribution, okay, if the random walk can be normalized and get in the limit a stable distribution. Okay? Well, we say something similar for the maximum. So if we take the maximum of copies of random variables, so this happens if and only if there exists an and bn sequences such that the maximum of I1, I2 up to In minus An over Bn has a non-degenerate limit as n goes to infinity. Okay, and I1 or Ij for j positive are IID, independent, identically distributed random variables. Okay? And here again, there are some conditions on the behavior of this random variable that are available to study this, for instance. Okay? Or vice versa. If we know something for this, we get something on I. Okay? So we can always play that game. Have something on the exponential, on the positive self-similar Markov process and transfer it into something on psi. In this particular case, on the exponential functional of that Lévy process. Okay? And something that is quite interesting is that this measure can only be of 3 possible types. is either an exponential random variable, either a beta distribution or a Pareto distribution. So lambda tilde can only be either exponential, beta 1 gamma for some gamma, or Pareto of some parameter gamma for some gamma strictly positive. And that we know it because of this theory of domains of attractions. Okay. Okay, this is one of the things that is available, for instance. Okay. Katsu? You seem surprised. Is it okay? Yeah. Have any questions? No? You're fine? Sorry?
So as I enter independent copies of I.
Yes, these are, oh yes, yes, yes. I, J has the same law as I.
What's T0 again?
T0 is the first hitting time. T0 is first hitting time of 0 for x. And remember, the first hitting time of 0, okay, has the same law as the exponential function, because it's the Lamperti transform. Yeah? Thank you. Okay. Okay. So we can connect the theory of exponential functionals with the theory of maximum domain of attractions and get some estimates for that. Okay. Another one is when psi is a spectrally positive Lévy process. And by that, remember, we mean that the Lévy measure on the negative axis is 0. Okay, so there are no negative jumps. Okay, only positive jumps. In that case, we can take the t to be tau y minus, which is the first time where psi t is smaller than y. Okay? Again, tau y minus is equal to plus infinity if the set is empty. Okay? That could happen if we have if psi has a finite lifetime, we may not go below 0 before the exponential time. Okay, but if the lifetime is infinite, then this will always be finite. Okay, take it as that. So the process is going downward continuously, and then upwards by jumps. I mean, the jumps can only be positive. If there are jumps, they can only be positive. Okay. These are some of the favorite processes of Kasu. Okay. So we reach all the levels continuously. Okay. So psi of tau y minus is equal to y for all y negative, for all y if tau y minus is finite. So if we take y smaller than 0, we have that I can be written as the integral between 0 as tau y minus exponential psi s ds plus exponential of y times a copy of I in the event where tau y minus is finite, I tilde. Okay, so in particular, if q is equal to 0, tau y minus is always finite for all y. Okay, and then I becomes this. Okay, and this means that I is a self-decomposable random variable. Okay. And so, in particular, I is an infinitely divisible law, okay, with Laplace exponent or with the Laplace transform of the following form. This Laplace transform is the exponential of minus the integral from 0 to infinity, 1 minus exponential of minus lambda x and some function k of x dx. It's just dx. Yeah. Okay. It's just dx, Professor Sato. It's just dx, or is kx dx divided by x, isn't it?
kx over x.
Yeah. Okay.
K is
Yeah.
decreasing.
The k of x is decreasing. Yeah. K is a decreasing function. And in fact, k of x is the Lévy measure of some process y, okay, for x positive, where pi is the Lévy measure of y, a Lévy process such that I has the same law as the integral between 0 and infinity of exponential of minus s d ys. That is a property of self-decomposable random variables. Okay, every self-decomposable random variable every self-decomposable random variable can be written like that. Yeah? That, please check the book by Professor Sato, chapter 20 something. I don't remember exactly which one. In this case, Y is a subordinator. Y is a subordinator. And Yt can always be written as the sum of the jumps. Okay? And a jump in Y can always be written as the integral between tau Y minus and tau Y minus exponential psi s ds. So, to see why this is true, we take the path of the process Y, the process psi, okay, yeah, and we take the excursions, but the excursions of psi from the infimum okay, are the excursions of the process when we pass below a level. Okay, so when we pass below level y, we start excursion. Okay, and this excursion we integrate it in an exponential. Okay, to get the jump. So we have an explicit construction of y. Okay, but that is not so explicit to get this. Okay? So one problem is get explicitly k. Okay? So we know in this case the exponential functionals can be studied using the theory of self-decomposable random variables, but we need to get explicit construction of this pi bar. Okay? But at least it's another tool that is there available. And that's helpful because if we know the asymptotic behavior of this random variable, then we can get the asymptotic behavior of this function k, then we can get the asymptotic behavior of the tail distribution of I. Yeah? So, k determines the behavior of the law of I. Okay? So it's important to determine this. So it's important to understand these excursions from the infimum for this process. Okay. These are just two examples of stopping times. Maybe if you have to study these exponential functions, you will find a clever stopping time that helps you to determine something, to get something about an exponential function. Okay, so that is about what happens for perpetuities. Okay. There is a paper by Bertoine and Jor, and a paper by Carmona, Petit, and your, okay, were, in fact, yeah, this paper of Berton and your, no. There is a paper by Carmona, Petit, and your, where they studied several properties of I, okay, and in particular, they prove that there is a density so the probability of I being in dy is equal to some function py dy, and this function p should solve one equation, okay? P solves the equation minus sigma squared divided by 2 derivative of x squared p of x plus sigma squared plus 2 plus a x plus 1 px plus, no, equal to the integral from x to infinity of pi from minus infinity log u divided by x p of u du plus integral from 0 to x pi from log of x divided by u infinity k of p of u du for all x strictly positive, okay? That's a tricky equation. It can be useful, in particular when pi is 0. This can be solved explicitly, but in general it's rather difficult because we have an integral differential equation, okay? In the particular case, when pi is equal to 0, this equation can be used to show that the exponential functional of exponential sigma Brownian motion minus bt dt for b positive and sigma positive, sigma real. It doesn't change if you take positive or negative because Brownian motion is symmetric, okay? Then this random variable has the same law as 2 times alpha, yeah, if I take alpha, but I don't take alpha, so sigma square a gamma random variable with parameters 2 beta sigma square, okay? Where gamma of lambda follows a gamma distribution of parameter lambda, okay? This is something that was proved before by Dufresne and other people, okay? And in fact, we can use the theory of Bessel processes to determine this law because this is the first heating time for a Bessel process. There's first heating time of 0 of a Bessel process, okay, of some dimension. Okay.
So this like P is always differentiable, or?
It happens, yeah. Yeah. The differentiability of P related to to this sigma square. In fact, if sigma is strictly positive, this is 2 times differentiable. In fact, in the paper of Carmona, Petit, and Yor, they prove that P is of class C infinity. Yeah. Yeah, thank you, Kas.
So there is always a solution to this.
There is a unique solution to this.
Problem.
Yeah, yeah. Solve the equation, and this is the unique solution. Yeah. Yeah, if you are bored on Saturday or Sunday, you can easily check this as an exercise. Like this. Okay. What else? There are many other. There are other cases where the law of I is known. It depends on the process you have, on the tools you have at hand. And there is a paper by Bertoine and Yor. Now, this is true, where they prove that if we take, let me just. If we take sigma, so if we take psi to be minus sigma, with sigma a subordinator, then the expected value of I n, so I remember, is minus exponential of minus sigma SDS. Okay, this can be written as the product from k equals 0 to n of k divided by phi k, where phi is the Laplace exponent of sigma. So the log minus the log of exponential of minus lambda sigma 1 when 1 is finite, when 1 is smaller than the lifetime of the process, is equal to phi lambda, and this phi lambda is a killing term plus a drift plus the integral term. Okay. This is also in Carmona, Petit, and Yor. Okay. In fact, they proved this equation first, this identity first. Okay, and this is useful because there are some cases where these moments are well known. Okay, and they are finite for all n. Okay, and also I is determined by its moments. Okay, and the main result in Bertoine and Yor is that there exists a random variable R associated to phi, okay, such that if I is independent of R phi, then the product I times R phi follows the same law as an exponential random variable of parameter 1. This E is an exponential random variable of parameter 1. That is quite amazing. And the moments of R phi are given by the product from k equal 1 up to n of phi k. Okay? And well, this is a result that they obtain in a very surprising way for me. But I think the inspiration they had for this result is coming from a particular case. When we take sigma to be such that Q is equal to 1 over gamma 1 minus alpha, drift we take it as 0, and pi we take it as alpha gamma 1 minus alpha exponential minus x 1 minus exponential minus x to the 1 plus alpha dx. Look, this is similar to what we get yesterday for the stable. Okay? Well, in fact, sigma is such that the Laplace transform of sigma with the index alpha, okay, is x. X is a positive self-similar Markov process, and this process and x has the same law as minus y with y, a stable subordinator of parameter alpha. Okay? So y is a process that starts at some point x and just decreases. Okay? And we kill it at the first passage time below 0. Okay? That gives us x. Okay? So we have that t0, which is the first time where t goes below 0, let's say starting from x. This is just the first time where, by construction, y is above the level x. Okay? In that case, it is known that if x is equal to 1, then t0 of 1 has the same distribution as an alpha stable random variable of parameter alpha. S alpha is a stable random variable positive of parameter alpha. Okay, so it's another stable. In fact, it's equal to y1 to the minus alpha in low. Yeah? Well, that is just another way to say that this random variable follows a Mittag-Leffler distribution. T0 of 1 follows a Mittag-Leffler distribution. Okay. Just a definition of the Mittag-Leffler distribution. And the moments are given by n factorial gamma 1 plus alpha n. Okay. And there is a nice paper by Schambach and Schrery in PTRF in the 80s, where they prove that this S alpha to the minus alpha multiplied by an exponential random variable independent of parameter 1 follows the same law as an exponential. Okay? Where E tilde and E are exponential random variables. E tilde is independent of S alpha. Okay? Well, there I must say that this is that was very striking, but I think Professor Mark Jor was aware of this kind of relations because he knew a lot about this kind of relations. He observed that, and he said maybe this is happening in general, and they came to this impressive result. This random variable, R phi, is such that the log of R phi is infinitely divisible. And in fact is spectrally positive. So the Lévy measure of this random variable is carried by the positive axis. Okay? And there are many properties about this random variable, and there is a paper by Alili and other authors, included me, where we study this random variable. Okay. I think I will exceed of 3 or 4 minutes. Just I wanted to finish this story. Is that this is not the only example where this exponential functional appears in some factorization. Okay. In particular, here there is a factorization of the exponential. Okay, but there are other factorizations. In what I told you before on the Jaglom limits, there is another factorization appearing. Okay? But there is more. There are other factorizations, and there are factorizations of the random variable I in itself. Yeah. Before I go there, I must say that in the literature you can find many factorizations of the exponential random variable. Okay, so that is a game you can play. Is you can try to identify each of the factors of the exponential that you find in the literature as the exponential function of some random variable. Okay, and that may become helpful because like that we identify the law of an exponential functional in particular. Okay. These factorizations of I that I will tell you, they are related to the Wienerhoff factorization of psi. Okay. This is coming from the following fact. It is known that if we take C to be the set of reals such that this exponential has a finite expectation, okay? These are not reals, these are yeah, that's okay. Yeah. Then if we take beta a complex number such that the real part of beta is in this set intersected with 0 infinity, then we have that the expected value of I to the beta can be written as beta over the characteristic exponent of psi in minus I beta times the expected value of I to the beta minus 1. Okay? So this identity that I have here, this one that I have here, is coming from a recurrence like that. Okay? This is what is happening in the more general case. Okay? This is the characteristic exponent of psi. Okay? And from there, if we have the Wienerhoff factorization for this guy, okay, we can guess, okay, that there will be somewhere appearing the characteristic exponent of a subordinator. So you will have a term like this appearing in that expression, and something else. Okay? That allows to guess so remember we have phi psi minus I beta that can be written as kappa of phi beta and kappa hat, this is h hat h of minus I beta. Yeah? The characteristic exponent can always be written as the product of two characteristic exponents. That is the Wienerhoff factorization of two subordinators. Okay? So if we plug that in here, we have that the expected value of I beta equal to beta kappa h I beta over kappa hat h I beta expected value of I beta minus 1. Okay? I'm not sure about the signs, but I will check that for tomorrow. Okay? But this term that we have here, okay, is appearing also in a relation in the Laplace exponent in the moments of the exponential functional of the negative of a subordinator. Okay? This I minus h is equal to the integral exponential of minus hs ds. Okay? So the fact that this term is in here and it is in here, okay, allow to guess the following factorization. That I should have the same law as I of minus h and times a random variable, but that random variable should be depending on this other guy. Okay? This is the product. Where I of minus h is equal to the exponential of minus hs ds, and jh is an independent random variable. Okay? And this is something that turned out to be true, and that was checked by Savov, Pardo, and Patti. Okay? And the random variable jh happens to have the following law. jh hat oh, okay, is such that yeah, the probability of jh is in the y is equal to y, the probability of r h hat in the y times a constant. Okay. Yeah, I was wrong with the signs. I said that. In fact, this is hat, this is no hat. Okay, so this, yeah, this has a hat. So please, this has a hat already. Minus, minus. This has a hat. So this has a hat. This has no hat. Okay, this has a hat, and this has no hat. Okay, and this RH is such that I of minus h times RH follows an exponential distribution of parameter 1. Okay, and there is more that can be said. It can be verified that we have another term appearing, which is that I will also have the same law as the exponential of the supremum of the process times I h hat minus h hat divided by r h, okay, all independent, and S supremum, infinity is the supremum of the process I in the whole path. Okay. So all this analysis becomes very useful now, because this random variable that is very hard to study, okay, can be studied in pieces. Okay, this one has moments that are known, let's say, explicitly. This one too, okay, and this one is also something that we know it's slow. Okay, and if we cannot determine these three random variables explicitly, we can at least study some properties of this random variable. For instance, we can check that the big values of this random variable are actually coming from these big values of this random variable. And that is to be expected, because if you take exponential of psi s ds, the big values of this integral should come from the big values of this one. And the big values of this one are this one. Okay? So for instance, it can be proved that the probability of I being bigger than t is like t to the minus alpha, so it has a heavy tail. Okay? If and only if the probability of exponential of s infinity being bigger than t is of the same form. Yeah? And it can be checked that the small values of this are coming from the small values of this one here. Okay? So it can be verified that the probability of I being smaller than t is equivalent to the probability of I h hat minus being smaller than t. Okay? In some setting. In the same setting of regularly varying. So when the probability of I is more or equal than t is like t to the beta L hat of t for some beta positive, and L, all the L's are slowly varying functions, and L tilde, L hat are slowly varying functions. Okay. Well, with that I finish the lecture today. But there are a lot of things to be said about these exponential functionals. Okay. It's a very exciting world, I would say. Are there any questions or comments? Sorry for exceeding the time.
So which ones are easy to simulate?
Sorry?
To simulate occasionally?
I think.
But that's not enough as you want.
Sorry?
So you want to simulate I, right? So you need.
Okay, I want to understand this random variable, but making simulations of it is quite it's quite difficult, I will say, as it is for these two. Maybe the one that is available is this one, but still. From the computational point of view, all of them are hard to compute, to determine or to understand. But at least distributionally, so if we want to get some property of the distribution of this random variable, we can try to get it from one of these. That's a point. I mean, it's a kind of Wiener-Hoff factorization, because in fact we are splitting the support of I, okay, with this factorization. Okay. This will determine the support near zero, and this is support near infinity. Essentially, these two near infinity. Okay, thank you very much.